consider this triangle right here. We all should know in respect to what angle they're talking to, this side is adjacent. So if they're talking about this angle up here where my mouse little trigger is, if they're talking about that angle, this would be the adjacent side and that would be opposite. So you have to go into respect to what angle you are trying to figure out. So remember that. And then this is always 90 degrees. So that should be known already. I don't want to say that like an old traditional professor, but I'm hoping everybody's had geometry or at least seen this maybe in junior high. But that's the right angle. And the total sum of the angles of a triangle should be 180. So hopefully we know that a little bit, what a right triangle is, and the sum of the total angles should be 180. Now they say consider a triangle with theta. Theta, this is just a Greek symbol, as one of its acute angles. The trigonometric ratios are defined as follows. So here we have sine is related to opposite over hypotenuse. So that's where that so comes from, right? Hopefully, if you haven't heard of it, this is where it comes from. Now we're considering cosine. That's going to be the ratio of adjacent versus hypotenuse, which is ca. And then tangent is a ratio of opposite over adjacent, which is toa. So katoa, maybe that's why I've said before, try to find something funny, cute to help you remember. And if you know the first three, the other three are going to come real quick, because if you notice, they're just the reciprocals. You just flip them. Notice for sine, he's opposite over hypotenuse. Well, and we take the reciprocal of sine, 1 over sine. 1 over sine is cosecant. 1 over sine is cosecant. We should know that by now. So cosecant is just hypotenuse over opposite. So we know the first three. We know SOHCAHTOA. We know the other three. That's what's good about some parts about mathematics, right? If you know some parts, the others come easily. But the hard part is knowing that part. So I see somebody's not muted. So let me go ahead and mute them. All right, let me check my settings once more. All right, so that's pretty much what this slide is trying to explain. So again, you have to go into respect to which angle you are calling or which angle you're looking for, and what side you're going to call adjacent, what side you're going to call opposite. And again, the longest side of a triangle is always the hypotenuse. All right, so here they give us an example of a triangle that has been blown up by a certain ratio. So the symbols we use for these ratios are abbreviations for their full names. Obviously, SIN is sine, COS cosine, so on. Since any two triangles angle are similar, these ratios are same regardless of the size of the triangle. Again, since two right triangles with an angle are similar, these ratios are the same regardless of the size of the triangle. So the trigonometric ratios depend only on the angle theta. So here we have a triangle. We have a small one and we have a bigger one, obviously, right? See, we have 4, 40, 3, 30, 5, 50. So it looks like it's been blown up by a factor of 10, right? So if they considered sine, remember sine, right? Opposite over hypotenuse. So it's in respect to this, so it's opposite. So opposite over hypotenuse. Hypotenuse is 5. All right. And they illustrate the same exact thing right there for that triangle that's blown up. So here they're just talking about how these angles are similar right here. Since any two right triangles with angles that are similar, with an angle similar, these ratios are the same. And what do you know? What do you know? What do you get for sine? 3 over 5. 3 over for initially we get 30 over 50, but when we reduce, as always, as necessary, we reduce when all the time. We may forget that might be -1, or I'll look the other way. But reduce when necessary, and look how we get the same ratio, 3/5 and 3/5 as well. All right. Moving on. What do they want us to do here? So let me zoom out a little bit. Let me zoom out a little bit. So here, what do we have? Zoom out right here. Zoom out. So here they want us to find 6 trigonometric ratios of an angle theta. So here they give us some information. We know this is 90 degrees right here. We know this is 90. We don't know what theta is. Since we don't know what theta is, we can't find out this other angle is. But here they just want us to find the ratios of the angles. So that's good. Let's go ahead. We can go back to slide 5 if we forgot already, and we're gonna find the 6 ratios of the triangle that was given. So let's go ahead, and I'll write SOHCAHTOA over here, right on the top. SOHCAHTOA, just to let us. So I want to write the whole thing, right? I don't got a lot of space unless I make any slides, so that's not a problem. So let's go ahead and play with this one. So let me delete, or at least move solution. I can't move that up. Let's move that up. All right, perfect. So we know sine. Sine, we have so. All right, so for sine, we have that opposite over hypotenuse. So we're in respect of this angle theta. Looks like let me go ahead and label my triangles, right? So that would be opposite. I'll use ADJ for adjacent. That's my adjacent side. And then obviously, the longest side of the triangle is your hypotenuse. And also, I forgot to mention, if you don't know this yet, the hypotenuse is also the opposite side of the right angle. So if you know where your right angle is, just look across it and you find your hypotenuse. And then, into respect to what angle you're talking about, you label your adjacent and your opposite side. So we know sine. We know sine. We don't know what theta is. We don't know what theta is. So sine of theta is going to be opposite over hypotenuse. So opposite is 2 over hypotenuse, which is 3. And that's all they're asking for. So we got 1 down, 5 to go. We can do cosine. Let's just go ahead and find the first 3. Cosine of theta. Cosine of theta. All right, cosine of theta, I believe, is going to be adjacent. Adjacent happens to be square root 5. That's okay. Over the hypotenuse, which is 3. All right. Now, tangent of theta. Tangent of theta. I believe that's TOA. That happens to be opposite, which is 2, over adjacent, which is square root 5. So it's okay. We'll leave it at square root 5 on the denominator. I know we can rationalize this and multiply by square root 5 or square root 5. But if this was an application problem, they would more likely want us to find the angle or the side of a triangle rounded to a certain amount of decimals. So in this section, you may see a lot of square roots on the bottom, but generally we do not like to see them. We rationalize just like we did in chapter 5. I believe when we have like pi over 3, tangent of pi over 3, we need to rationalize to get square root 3. So you may see another square root in the denominator, because since I know sine, the reciprocal sine is cosecant. Cosecant of theta. And reciprocal means you just flip. So all I got to flip, excuse me, all I got to flip is 2 over 3. So now I got 3 over 2. Notice how I said it was very easy. If you knew the first 3, the other 3 come just fairly easy. Now, just got to remember the reciprocals of the first three trig signs, which we should know by now since chapter 5 is passed. So secant is the reciprocal of cosine. Secant. So try not to get confused when you take the reciprocal of cosine. Don't think cosecant, right? Reciprocal of cosine is secant. Let's go ahead and take the reciprocal. We get 3 over square root 5. And excuse me. And last we get cotangent. Cotangent. Take the reciprocal, flip the fraction we have up here. We get square root 5 over 2. So this is a good exam problem. See if you can come up with the 6 trigonometric ratios here. So not bad. So if you were asked to do that, I think this would be fairly easy. A few minutes just to come up with these 6 ratios. Nothing too serious. Now we have our special triangles. So here we demonstrate a box and then how we can draw a line to that box diagonally and how it forms 2 triangles. And keep in mind, let me say we draw a square. Square has 4 90-degree angles. Keep that in mind, right? A square has 4 90-degree angles. I can draw them myself, right? Not the best drawings, right? Not the best drawings. But at least they drew one for us, right? So I'll erase mine. I'll let theirs be there. And they also want to illustrate that. So let me go ahead and go over the literature here for the special triangle. Certain right triangles have ratios that can be calculated easily from the Pythagorean theorem. So I'm sure some of us remember that. The Pythagorean theorem, right? The a squared, the b squared, and equals c squared, right? Something. Just want to just keep this open. Make sure hands ain't being. Make sure a hand is if a hand is raised, I can see it. So we know Pythagorean theorem is a squared plus b squared is equal c squared. So in this course, we're going to see an extension of Pythagorean theorem, and which is known as Pythagorean's identity, which is very heavy. If you continue to learn, you continue your studies in mathematics or even in computer science. You don't need to know too much math in computer science, but you need to know your math in computer science. So certain right triangles have ratios that can be calculated easily from the Pythagorean theorem. Since they are used frequently, we mention them here. So the first triangle is obtained by drawing a diagonal in a square of side 1. So this is the first special triangle. I'm sure you heard of those special triangles right here. 45, 45, 90. I'm not too sure if that strikes or rings a bell. Rings a bell when I was in my geometry class in high school. Had a teacher would say special right triangles, 45, 45, 90. That's one of the special right triangles. So what they mean is a triangle that has 45 degrees, and then a 90 degrees. So 45 plus 45 is 90. 90 plus 90 is 180. So here they get that special triangle by drawing a box. I'll draw my box as best as possible, right? And of length 1, right? Of length 1, each side is length 1. They draw that diagonal such that it's perfect. Remember, this is a 90-degree angle. If this was a 90-degree angle and this is a perfect diagonal, so it cuts that off and makes this 45 degrees. All right. So, and if you want to know where that square root 2 is, it's coming from the Pythagorean theorem. We have a squared plus b squared equals c squared, which is going to be the hypotenuse. So here we have 1 and 1 and 1. If you're wondering where that square root comes from, 1 squared plus 1 squared is equal to c squared. That obviously is going to just become 2. Because 1 squared is just 1 plus another 1. And then to get rid of that square, we square root such that the hypotenuse, right, c is equal to square root 2. So that's where that square root 2 comes from. So that's the first triangle we get by drawing a diagonal of a square of side 1. So here's our 45, 45, 90 triangle. Then we have another triangle here. But excuse me, by the Pythagorean theorem, this diagonal has a length square root of 2. The result of the triangle has 45, 45, and 90 degrees. Or if we were in radians, pi over 4, pi over 4, and pi over 4. So to get the second again, they're talking about what we did earlier by the Pythagorean theorem, the diagonal. They're talking about this diagonal right there. The diagonal is drawn is technically the hypotenuse. So hopefully that didn't confuse anybody. The diagonal technically is the hypotenuse for both triangles, the blue and the red one. So hopefully that didn't confuse anybody. And then we found the angles 45, 45, and 90. But remember, we know how to convert. So try to get a little bit familiar with at least the quadrant 1. Quadrant 1, get familiar with those radians and angle degrees very fairly, because those are frequently used a lot. As for the other ones, well, we do have the formula to convert radians to degrees or degrees to radians. So 45 degrees is pi over 4. And that's the one we should remember the most, because those terminal points are square root 2 divided by 2, comma, square root over 2, right? So, and 90 degrees happens to be pi over 2. So, but usually when we're dealing with triangles, we do not use pi over 4, right? We wouldn't call this angle pi over 6 or pi over 2. We wouldn't call it that. We deal with degrees here. So to get the second triangle, we start with an equilateral triangle, and they call this a triangle A, B, C, right? Not the best drawing, but okay, illustrating how they drew triangle ABC. So to get the second triangle, we start with an equilateral triangle ABC of side 2. Okay, all right, of side 2. So if this side is 2, this side, what did I do here? Mm-hmm. Mm-hmm. Gonna exit, escape. I don't need that. File. What did I do wrong? Let me save it and then close it. Oh my god, technical difficulties. What's the name? Just 928. 928. Let's close this. Good, it's gone. All right, back to where we're at. Back to the saddle again. Right. So then here all right, this is again not what I wanted, but we can zoom in a little bit here. How do I close this? Does anybody know how to get out of this mode? I think it's. Can I draw? No, I can't. No, I don't want that. I cannot draw that. Can't draw that. Oh man, I can draw like this, but I would have to. Oh. Can everybody see at least okay? Let me turn on the chat. Can everyone see okay?
Yes, Mr. Villalpando, it's good.
Okay, all right, okay. Like I feel bad because you're on a small screen. All right, good. All right, so going to our second special triangle. I do apologize. Here we're talking about this one. Here we're wrapping up about the first triangle, 45, 45, 90. Again, in radians, it's pi over 4, and pi over 2. Now, to get the second triangle, we start with an equilateral triangle, equilateral, hence every side of the triangle is equal. Every angle is equal. 6, 12, 18. So 60, 120, 180. So every angle is equal, every side is equal, hence equilateral. So to get the second triangle, we start with an equilateral triangle with side 2, so that's 2, and they draw a perpendicular bisector through D and B. So they're talking about this red line that runs up and down here. So if that perpendicular perfectly splits that triangle in half, then that side is 1 and this side is 1. All right, so that gives us a little bit of information here. Try to dissect, right? Try to read in between what they're saying. I know it's hard with math because math is another language, even though it's already in English. Itself is another language. So I know a little bit what's going on. So I know if this was a straight line, right? They help us out too a little bit. They told us this is 90 degrees. We know this is an equilateral triangle, so every angle is 60 degrees. So they gave us a hint right there that this is 60. This is a perpendicular bisector. So they helped us out. So that's 30 degrees, and this other half must be 30 degrees as well. So they're giving us a little bit of help here. I'm not too sure if they want us what they want us to find. So let's take a look at that. Now it says Pythagorean theorem, the length of dB is square root 3. So let me take a peek at that. So, okay, this square root 3, they went ahead and used Pythagorean's theorem. Since we know, it can't work too much because this side came out. Since we know this side is 1, we know this side to be 2. We know this side to be 2. We have that to be 1 squared plus b squared is equal to 2 squared. All right. So here we get 2 squared. So 1 squared is 1 plus b squared is equal to 2 squared, which is 4, minus 1 gives me b's square is equal to 3. And let's go over here. B squared is equal to 3. Apologize for my 3 over here. And then solving for b, we get square root 3. So that's where that square root 3 came from. All right. So now we get a better understanding what's going on with this second triangle here. All right. So this one's the 30, 60, 90 triangle. So this is a 30, 60, 90 triangle, another special one because we get the total sum of 180 degrees in that triangle. So this starts off with designing an equilateral triangle of side 2. So it says by the Pythagorean theorem, we got square root 3, what we just did right now. Since DB bisects the angle ABC, the triangle ABC, since DB bisects ABC, we obtain a triangle with angles 30, 60, 90, what I mentioned early, or in radians, pi over 6, pi over 3, pi over 2. You can double check if you like in your side with the formula. Remember, it was just 180 over pi or pi over 180, depending on where you wanted to get to. So again, this would be 30 degrees. This would be 60 degrees. And this would be 90 degrees. Okay, so far so easy. Hasn't been too tricky. It's kind of kind of remedial if you think about it, if you've already taken a geometry class, but it builds. That's the problem. It builds to the law of sines and cosines. So that's when we don't have right triangles. So that's why it's been so much fairly easy. Now it says we can use these special triangles in figure 5 and 6, which let me see if I scroll down right here, figure 5 and 6, these two triangles. We can now use these special triangles in the pictures down below to calculate the trigonometric ratios for angles with measures 30, 45, 60, or power 6, power 4, and power 3. So using these two methods of coming up with these two special triangles, we're able to come up with these special angle triangles, right? These two special triangles, right? The 45, 45, 90, and here we have a 30, 45, 60. All right, so that. Oh, okay, it's leading up to the special. Okay, all right, so there we go. Here, they're just trying to illustrate here that it's the same thing. It depends. Your calculator, remember I said, depending if you're in radians or in degrees. Radians or in degrees. So if your calculator's programmed in radians, if you do sine of power 6, you get 1/2. Now, if it's in degree mode, sine of 30 would give me 1/2 as well. So let me pull up. We have that in our unit circle. We have it here. So hopefully some of you have printed it out. Notice how 30 degrees relates to pi over 6, right? Starting with our positive x-axis. So notice how certain angles, whether it be in radians or degrees, they're going to give you the same terminal points. They're going to give you the same terminal points, and that's what this slide is trying to illustrate here. And we saw a few tables like that in chapter 5 as well. So my favorite usually is tan of 45 because it equals 1, because the terminal point, let me open that up. The terminal point for pi over 4 or 45 degrees is square root 2 over 2, square root 2 over 2. You divide in the same thing, you get 1. So that's why I say it's my favorite, tan of 45 or tan of pi over 4, because I know it's 1. And the same thing goes for cotangent, because it's a reciprocal, it's the exact same thing. So depending on what you're working with, you end up with certain ratios here. Notice how they don't have square roots in the bottom. It's okay if you do. If you do, that shows me that you have enough knowledge to execute the problem. Maybe not just simplify by one more extra step, but you have the exact knowledge to solve the problem. So that's good. That's good, especially if it was an application problem. I told you the round to 3 decimal points. It wouldn't even matter if you had the square root in the bottom. You would have the exact same answer. So again, these work the same way depending on your calculator. And you can tell your calculator will say rad for short for radian, or it'll say DEG for degree, or it might even say the word degree. So be careful, because we're going to be switching back and forth in this section from radian to degree. So be careful. Now, what do we have? Some information here, some more literature. So to find the values of trigonometric ratios for other angles, we use a calculator. Mathematical methods called numerical methods used in finding the trigonometric ratios are programmed directly into scientific calculators. Calculators give the values of sines, cosines, and tangent. The other ratios can easily be calculated from these by using the following reciprocal relations. So if you wanted to find the cosecant of a certain value, you can do 1 divided by sine of that value, but you don't need to, right? If your calculator already has cosecant, secant, and cotangent programmed into it, you don't need to do the 1 over sine, 1 over cosine, or 1 over tangent. So depending on the calculator you have. It's very basic. It might just have sine, it might not even have trig on it. It might just be a simple four function calculator, add, subtract, divide, and multiply. So be careful. Casio is a good calculator. It's about $15. Don't, or you can, if you can get one provided free. I don't know how that would work. With the school district, and I'm not too sure. Not too sure. All right. So let's see. All right. So all right. So are we building our way? Let me see. Are we building our way? No, not yet. Not yet. So we haven't seen Pythagorean at the end. I thought we did. All right. So when we follow the convention that when we write sine t, we mean sine of the angle whose radiant measure of t. So for instance, sine 1 means the sine of an angle whose radiant measure is 1. So when we're dealing with sines and cosines, we're dealing with angles pretty much, right? The sine of this angle gives me this value. So that's why with the unit circle, let me pull that up, we're using t first instead of saying cosine of x and y. We're using t because pretty much sines and cosines, we're evaluating angles. Even though if it's pi over 6, pi over 4, or pi over one of these possibilities you may see, you're pretty much evaluating angles. All right. So for instance, sine 1 means the sine of an angle whose radiant measure is 1. So when using the calculator to find the approximate value for this number, set your calculator to radiant mode, and you'll find that sine of 1 is just going to be some decimal value. Because if you look at the calculator, the unit circle, it doesn't really work off sine of single digit numbers, right? It works off sine of angles. So, but sine of single digit numbers do work because they're in radians. So that's fine. So if you do sine of 1, it's going to give you some numbers. Hopefully, if you're following along, we'll follow to a few decimal points. So here we get 0.841, and let's give an extra 471. So again, it's approximation. So that's in radians, though. So be careful. That's in radians, right? Now, if you want to find the sine of an angle whose measure is 1 degree, right? Set your calculator to degree mode, and you'll find that it's going to be a little bit different. So radians and degrees are different, right? So again, I was going to do an approximation. So it's already there for me. So here you get 0.0174524. So actually 1 degree is a lot less than, not significantly low, but it is 0.01. So I do consider it, a lot less. So it's a lot less, so it's different. So be careful when your calculator is in radian or degree mode. So if you're sine of radian 1, you get 0.84, but if you're sine of 1 degrees, you get 0.012 if you round this the 1 to a 2, because the 7 right here. All right. So be careful. They're just here trying to illustrate the difference between radians and degrees when you plug them into your calculator. All right. Applications of trigonometry of right triangle. So I think we're leading up almost to our last example. I think we may have 1 or 2 for this section. Right. A triangle has 6 parts. Hopefully we have intuitively picked that up. 3 sides, 3 angles, right? 3 plus 3 is 6. To solve a triangle means to determine all of its parts from the information known about the triangle. That is, to determine the lengths of the 3 sides and the 3 angles. So like what I just mentioned, the 3 sides, 3 angles. I think that one was straight obvious, right? When you look at a triangle, I don't think you need a book to tell us that. So in this particular triangle, we have A, B, C, all right? We get our triangle. So let me erase that. Not so pretty, right? So this particular triangle shown below, what do we know? We know the hypotenuse. Let me label a little bit of stuff. I haven't even read the question, but I like to dissect what I have first. So I know this is my hypotenuse is 12. I don't know my legs. I don't know A and B. I know this is 30 degrees. I know this is 90. I know this is 90, right? So to find this missing angle, I think we can do 90 plus 30, right? Because the total sum should be 180, right? So 90 plus 30 is that 120? 120. And then 180 minus 120 is that so is that 60? I think so, right? 60. 60. Right? So here we have 60, 30, 90. So we have a 60, 30, 90 triangle here. All right. So we found a little bit of information. We know all our angles. We know one side. Let's see what we can do. They say it's clear that angle B is 60 degrees. Why? Let me forget. Don't forget your degree sign, right? I forgot my degree sign. I hadn't even read that part yet, but I wanted to just figure out as much as I could about the triangle presented, even before I read the triangle. I wanted to understand it first before I find what they asked me to find. So they say it's clear that angle B, again, this stands for angle C, angle D, refresher from geometry if you don't remember. So it's clear that angle B, it's a notation geometry, angle B is 60 degrees. To find A, this side, right, this side, to find A, it says we look for an equation that relates A to the lengths of the angles that we already know. So in this case, what do you think we have in mind in this case? Think about the SOHCAHTOA. Think about SOHCAHTOA. SOHCAHTOA. All right. So the reason why I'm talking about this is because we can help find what they're looking for, which is side A. So think about SOHCAHTOA, and I want you to think about the ones that have the hypotenuse, the 8s. So let me fix this one. All right. And then we're in respect to this angle. Don't matter what angle you're in respect of. You could use adjacent. You could use so and ka, I believe. Let's use sine. I believe you can use that should be fine. Opposite. So they should be fine using both. You should be fine, but let's go ahead and use sine. So remember sine was related to I believe opposite over hypotenuse. Recall, right? Do you remember? So let me make a new slide here. New slide. Copy this triangle. So here we have this new guy. We know that we want to use sine. I have this angle. We could use this. We could use cos as well, but sine's all right. I like sine. We know sine 30 degrees is going to be related to opposite over hypotenuse. All right. We know this is hypotenuse. We know this is the this is opposite. This is opposite, right? All right. And now we want to solve for A. A is opposite. You can again, I can put A if you like. If that helps there, right? We're solving for A. They wanted to find A. So let's go ahead and solve for that. Hypotenuse, which is abbreviated HYP. I think we know that to be 12. So let's go ahead and plug that in. And we're almost close to solving for this. Now, this is just a simple algebra technique that we need to do. A is trapped because there's a 12 underneath him. A is being divided by 12. Opposite of division is multiplication. Let's multiply. on both sides. It's kind of like a seesaw, right? If you do one thing to an equation on one side, you have to do it to the other side. And when I'm talking about when you do an operation, when I say one thing, if you do an operation on one side of the equation, you should do the same operation on the other side of the equation, because now we get 12 and 12 that cancel out. And then we're just left with A is equal to 12 times sine of 30 degrees. 30 degrees. And I believe now we can solve that, right? Can't we? Right? So to find A, we look for the equation that relates A to the lengths of the angles that we know. In this case, I went ahead and used sine 30 degrees is equal to opposite over hypotenuse, which is A over 12. Solve for A, not just yet, because I need your calculators to be in degree. Once they're in degree mode, sine of 30 degree, and even you don't even have to, if you know your quadrant 1, you don't really need the again, this is if you really know your unit circle, because if you look at sine of 30, let's look at 30 degrees, sine is related to the y part of the angle, that's 1/2. So if you're really great with your unit circle, sometimes you're faster than the calculator. So then that becomes A is equal to 12 times 1/2. Question, Ethan?
I just had the answer. Or
Oh, okay. Yeah. So basically now we just need a half A, and you got 6. Is that what you got? Is that the same thing you got?
yeah, that's what I had.
Yeah. So now that we know A is 6, we can figure out the other side as well too. So let's go ahead, and it says similarly cosine of 30 degrees. Oh, so here we want to find B, right? So let me go ahead and copy the triangle. So similarly, we can finish off our work and find B. So we know A is 6. We can scratch out A, right? We know this is 6 right there, right? So we proved that already. So here they went ahead and used, I believe, right? So cosine of 30 degrees, cosine of 30 degrees. Let me write that. Is adjacent, so B over hypotenuse, which is 12. So no, the sine was the one we're gonna have to use. All right, that would have solved B if a I saw the H on both, so I assumed that they would work. So no, that would have found B. Then we could have just easily found A right after. You could have used Pythagorean theorem as well, but the book suggests to use these special formulas to find the sides. So here again, multiply by 12. We get B to equal 12 times cosine of 30. Now you can plug in cosine of 30 into your calculator, or if you know your unit circle, cosine of 30 is square root 3 over 2. So then we get the following. B is equal to 12 times, that's square root 3 over 2, right? Which becomes 12 square root 3 over 2. Reduce. 2 goes into 12 6 times. We get 6 square root 3. So that's what this side would be. And I know 6 square root 3 is not meaningful because that doesn't tell me how long that triangle or how long that side of the triangle is. But once this becomes an application problem, they'll ask us to round to either 2 or 3 decimal points. So this is we're getting to the main idea of how to play with these formulas here, and not so bad. So what gives students the most trouble, what I've seen, is fractions. So here I like to think about telling students the seesaw method, whether to balance it, you need to do it on both sides. So here we multiplied by 12 and canceled that fraction out. Here we still have a little bit more. One last example. I would like to finish, but we have about 5, 6, 7 minutes left. So let me go ahead and just take a look at how long 6.3 is. Let's take a look. It's 37. 37 slides. All right, so let me just try to wrap this up. Let me, I guess, lock the meeting. There's a chat. Let me lock it for now because the college algebra students might come in. So I think we can finish this last because the next one, the 10.3 has like 30 slides. So we just have one more example left. It says to discuss the next example, we need some terminology. So if an observer is looking at an object, say, then the line from the eye to the observer to the object is called the line of sight, right? The line of sight, right? Look at this guy. He's down here and he's looking at somebody here on some, I don't know the correct word. It looks like a pulley system there. Don't know the correct word for there. So that's his line of sight. And you can kind of think about right here, this being the positive x-axis right here. So his line of sight is looking up, and they call that an angle of elevation. So I like how they use that black line there. It's roughly a little bit small. But right there, think of that as the positive x-axis. And if he's looking up, then this has an angle of elevation. Conversely, though, if he's looking down, say this, notice how this was a little, could be a prank. He dropped the bucket of water on this person here, though. Try to make it funny. If their line of sight is now below the x-axis, they call that an angle of depression. So angle of elevation, angle of depression. All right. Zoom out a little bit, little terminology, and then the last example right after this. So if an object being observed is above the horizontal, then the angle between the line of sight and the horizontal is the angle of elevation, like we saw in the picture. And if the object is below the horizontal, then the angle between the line of sight and the horizontal is called the angle of depression, which again we saw in the picture here in slide 20. So if the line of sight follows a physical object such as an inclined plane or a hillside, we'll use the angle of inclination. So this gives us this last problem here. So it says a giant redwood tree shadows 532 feet long, right? Find the height of the tree, the angle of elevation. So, okay, right, angle of elevation. So that's going to be, well, we're going to be looking up, right? Here's our angle of elevation here. Find the height of the tree. The angle of elevation of the sun is 25.7 degrees. Let the height of the tree be h. So instead of using A, B, and C, they say h. We can use A, B, C. That's fine. That doesn't matter too much. So the first thing first is they say let from the figure 10 we see the following. So we can make this a little bigger right there. Right here we know a little bit of information. We know this is the angle we're in respect to. We're in respect to this angle. So this will be my adjacent, or I should write adjacent down here. Maybe that's a little bit better. This would be opposite. And then this would be hypotenuse. All right. So you're assigning an idea. So hopefully you're thinking right now, which trig, let me go ahead and write SOHCAHTOA again. SOHCAHTOA. So based on what I have, I want to find the height of the tree. I want to find opposite. Based on what I have, which trig one should I use? Right? So the most obvious one and the only one that makes sense is tangent, because tangent of theta tangent of theta is opposite, which we're interested in finding over adjacent, and we have adjacent already to be 532. So I'll write adjacent for those of you who are new to this. We already know theta. We know the angle is 25.7. So let's go ahead and finish this problem off for today's lecture. Perfect. So here, let me go ahead again and put tangent. Tangent of theta is going to be opposite over adjacent. So that D looks bad. All right, adjacent. So we know it's 25.7. So we have tangent of 25.7. And again, this is degrees. So fix that. This is degrees. Opposite, I don't know. We'll call it H. I know the adjacent to be 532. Let's solve one more time. So let's multiply by 532. What I do to one side, I need to do to the other side. So multiply by 532. So this cancels out. We're left in terms of H is equal to 532 times tangent of 25.7 degrees. So let's just go ahead and round. We'll round to the nearest foot. We'll round to the nearest foot. So here, H. So let me turn the chat on. Let's see if anybody else gets the same thing. Plugging this in, 532 times tangent of 25.7 degrees. Again, that 25.7 don't look so great. 25.7 degrees gives us to be careful. Are you in radian or in degree mode? Yeah, if it was, yeah, degree mode. Okay, did you type something wrong though? Because if the tree was 2,304 feet, that would be a ridiculously high tree, right? I don't know what the tallest tree is, but 256 approximately to the nearest foot. And we deal with feet here in the United States. We'll use feet instead of meters, right? Yes, 256. And that's the last slide we have here too. So now we should be able to do the homework here or finish off the homework here. That's good. So hopefully it's not too long. It's not too difficult. It's just dealing with those the 6 trigonometric ratios and just plugging in what you have. So 256. Therefore, the height of the tree is about 256 because we approximate it. So that leaves us with today's lecture. And then on Wednesday, we'll do 6.3. See as far as we can do. And then we'll, if needed, we'll wrap up 6.3 Friday and then open up exam 1 for this weekend. Angular and linear speed. There should be some problems already in angular and linear speed. Has anybody worked on angular and linear speed problems? Okay, so someone said they did. Yes, there should be some. So depending on the section you click on, you might find it on some sections are labeled different. Some might have only the trig. Some might have the graphs of the trig. Some might have the inverse of them. So you have to check. So we are done with 6.2. Perfect. Exactly what I wanted to do. 6.3, hopefully, I know it's a little bit longer. Hopefully we can get close to, if not, and then discuss, any question, comments, concern. Pretty easy, right, for this section. Pretty easy. That's why I say I believe chapter 6 is the easiest chapter, in my opinion, because it's just dealing with formulas. But the only thing is we need to know how to set up these formulas. So we are done for today. I hope everybody had a good time. Have fun every time. So let's go ahead and stop this